Hello, and welcome to this presentation on meeting the Industry 4.0 security challenges of IEC 62443. My name's Haydn Povey. I'm CEO of Secure Thingz. A little bit about Secure Thingz. We are part of the IAR Systems Group. IAR are the largest vendor of development tools for embedded systems, with over 1 million customer products, over 150,000 active developers, and over 46,000 customers globally, operating, of course, in all of the major marketplaces, as you'd expect: consumer, automotive, medical, IoT, and industrial IoT. First of all, it's worthwhile stating that security is far too important to leave to somebody else. It's central to the value of your company, your brand, your product. You have to take responsibility. There is no silver bullet or one shape fits all off-the-shelf solution. But the right tools and the right frameworks, such as IEC 62443, can make that implementation far, far easier. Leadership is really important here as well. And Gartner predicts that 75% of CEOs will become personally liable for cyber-physical systems and incidents by 2024. This is a huge change in approach. Potentially, there are over $50 billion worth of financial impact here. And by moving that from the companies to the leadership, we really bring this into focus. But as well as scaring our leaders, we also should look at how security delivers multiple high-value benefits around inhibiting malware, IP protection, production control, and secure identity and rapid onboarding. These are all high-value components of any product. First of all, it's important to inhibit malware through the life cycle. We probably all know this. It has real costs, real impacts, real lives. We've seen real hacks occur in industry and in hospitals, and these have a major impact on the industry. However, similarly, there's also an economic impact. It's estimated by the ECIPE that IP theft has had a 60 billion economic growth impact on the EU due to cyber theft. And annually, that equates to about 300,000 job losses. This is a huge theft on global scale. And of course, this impacts lots of industries. Electronic devices and sub-assemblies are the leaders here. Industrial systems, city infrastructure, pharmaceutical production are all subject to IP theft. And that requires that we enable a supply chain of trust. Today, it's estimated that over $500 billion worth of goods every year are counterfeited, cloned, or grey traded. And electronics are the #1 impact by value. Now, this, of course, has impacts just by the scale of the loss. But with industry in particular, there are follow-ons around the system failure and the impact on brand of that. The support calls that you receive and you're trying to fix it, and ultimately rolling trucks to go and service the customer. Then there's replacements and, of course, liabilities. And this equates to a many, many $1 billion worth of overhead every year. So how do we start to meet these challenges? Well, there are industrial standards evolving which enable better security by design across the IoT. And first and foremost amongst these is the IEC 62443. The industrial IoT standard has many components, going from components and chips and devices at the bottom, which is primarily where we live, up through the system integration of the industrial automation and control system, up to the policies and procedures and general policies, overarching policies, which somebody like the National Cybersecurity will set. But if we get the components right, if we get the security built into the foundations of the devices, then the rest of the layers become far, far easier to implement. If we look at the risk assessment here, this is the standard Plan, Do, Check, Act that we see from VDE. And of course, this starts with identifying assets, but it is a loop procedure. So we need to identify what we are protecting and then analyze the threats. Who are we protecting it against? What are the relevant objectives and what are the risks which come out of that? Is it IP theft? Is it the fact that somebody can compromise and own a system, etc.? We then need to look at the measures and assess the effectiveness and select those. Implementation is the challenging one because, of course, we can't go belt and braces in most systems because of cost. So we always have to form a balanced approach. What are we prepared to add in terms of cost versus the rewards and removing the low-hanging fruit that an attacker will go after? Once we've implemented these, we then need to perform an audit. We need to put it out into the marketplace, get feedback, and then start that cycle again. And of course, documentation forms a large central core of this loop. One of the core areas of this is that there are 4 very specific security level definitions, going from level 1 up to level 4. Level 1 is really just protection against casual or coincidental violation, and in reality today is just really good coding practice and good implementation practice. Somebody with simple means, low resources, low motivation, accidentally or casually impacting a system. So these are really configuration errors and making sure that passwords are enforced. And this really should be just the first thing on the to-do list of any modern project. Going up, we perhaps need to protect against disgruntled employees or simple malware bots. So relatively simple means, relatively low resources, generic skills, and again, relatively low motivation. These are not people looking at specific targets. These are people releasing bots in general. And again, just some good hygiene, making sure that our code is signed properly, will inhibit these being loaded. We then go on to level 3 and level 4, and this is really where the industry needs to be, with protection against ransomware attacks where somebody is really targeting your equipment, or a nation-state attack where we have some critical infrastructure. In both of these cases, we expect at least sophisticated means, some resources, some skills, and a moderate to high motivation. Now, of course, in most cases, if it is based around ransomware, financial, then we just have to be better than everybody else, and the attacker will go find another target. Of course, if we are in critical infrastructure, then we have to suspect that we will see prolonged, pervasive nation-state attacks occurring. So what are the functional requirements that we see? And on the left here, we see the IEC stack laid out as different components, and the 7 functional requirements. And what we'll see here is that we will focus on the IEC 62443-4-2 requirements for components, and focus down on the identification and authentication control and the system integrity, because the rest is really around very specific implementations of your application. So if we go into the identification authentication control, here you can see grayed out some application-specific components and in darker black, the ones which really are generic. So if we have a look at CR 1.2, we need to have software, process, and device identification and authentication. This is somewhat obvious to most people in this room. It means that we need to have signed and versioned code with ownership prescribed into it. We need to have a PKI-based root of trust and/or a physically unclonable function. Now, only more modern devices will integrate things like puffs. Obviously, a lot of devices, we need to lock them down and put in the PKI-based root of trust. But it does mean that we have to lock those devices, that we need to put in a level of functionality and close the tin to make sure that we even just meet that first requirement. CR 1.4, we need proper identifier management, and this is obviously a global unique identifier and proper X509 type certificate management. And again, this is good hygiene from a security perspective, but this is a very large departure from most embedded system development. We need to have authenticator management, leveraging the root of trust to deliver virtual TPM functionality, coupled with a proper key management system. We need to have that surrounding us. So as we provision devices, we have to be able to extract the keys and certificates. And then we need strength of password-based authentication. So in this case, we need to say, okay, if we're going to have passwords and we're going to have logins, they've got to be of a certain level. And obviously in a machine-to-machine context, those need to move to a PKI type implementation. As we move on to the second sheet of basic requirements, we need to have on 1.8 a public key infrastructure certificate. Now, there are obviously many different types of certificates out there, but at a basic level, these should be at least X509 or better type solutions for most levels. So this is for level 2, 3, and 4. Level 1 assumes, you know, we're just trying to do the base level hygiene. 1.9, strength of public key-based authentication requires that we have, validate the signature of the certificate, validate the certificate authority chain and the revocation status, has it been revoked or not, and map the authentication identity to the user. Can we trap that back to who we think it is? There are a set of other ones, again, which are application-specific, authenticator feedback, making sure that any response is obfuscated, ensuring that unsuccessful login attacks time out or hit a set limit to avoid just continual replay attacks, system use notification, so if we are monitoring and tracking our users, we have to let them know, and access via untrusted networks are coming in over the internet. We have to be aware of potential man-in-the-middle attacks and make sure that those are blocked. We then also need to have strength of symmetric key-based authentication, ensuring that we can establish mutual trust and securely store and utilize our symmetric keys as opposed to the PKI asymmetric, of course. Now, so far, so good. These, for most people in the conference, are not surprising requirements. But again, for those people who are building the components, these things have to become very simple. They have to become very usable and user-friendly, which is obviously challenging when we consider that we have a shortage of 3.5 million cybersecurity experts at a global level. And it's certainly our intent through Secure Things working with IAR to try and bring to bear the right tools so that any competent embedded developer can implement these requirements quite easily. As we look at the system integrity again, we have a number of requirements here. First of all, we have to communicate with integrity. So we have to have a robust root of trust based TLS or equivalent. There are many libraries which people can utilize today to achieve that, but it is a requirement, I think, even from level 1. We have to protect against malicious code. Now, this can either be code which has been altered ahead of programming time, as we saw with the CC cleaner, or with updates. And we need to ensure that we have proper signing and encryption of all code. Now, this is challenging in a microcontroller because typically there is nothing on that device to start off with. So we have to install either some secure boot management framework, or we have to leverage one of the latter technologies, such as the ST Micro secure firmware install, which ensures that there is a key provided to the OEM to ensure that it is a valid device and it is a valid code base. We have to do security functionality verification. We have to do verification of the identification. So is this what we expect it to be? Is the X509 in the right format and with the right data types that we'd expect? We need to authenticate and do use control without an unauthorized account, making sure that the simple attacks are all have countermeasures against them. We have to have software and information integrity. So ensuring the authenticity of the software, again, this is relatively simple at the first level. It is just a signature, making sure that we are signed properly. But of course, for most companies, that's a lot harder. Do they have the infrastructure in place to capture the signature properly? Is that on premise? Is that in the cloud? Is that through a third party? Or is that something under their control? And this becomes a much broader challenge. Now we have to have input validation, again ensuring that we don't have any out of range functionality, invalid entries or SQL injection. And again, simple tools can help with this. So if I look at the IAR range of tools, something as simple as the CStat, static analysis tools, will ensure that we can start to constrain and manage the inputs here. And then we also have to define a deterministic output. We have to ensure that if power fails or if a specific outcome is identified, that the system in an industrial perspective can fail into a known good state, that it's not left hanging, it's not left in a dangerous position. Again, these are requirements which any good system designer should be designing for, but unfortunately in many, many cases just doesn't happen. We have to assume that every device can be compromised, and therefore we have to be able to come back and recover to a known good state. We have to ensure that errors do not leak information, because the bad guys will obviously use all of that they can. In terms of secondary system integrity components, we have to ensure that from a communication perspective, we have enforcement and termination of unique sessions so that we are protecting the communications. And we have to make sure that audit logs and tools again, are protected so they don't accidentally leak information. As we come on to 3.10, again, these are fundamental requirements that every system now has to have. We need to have support for updates, critical requirement for all systems, presuming that every piece of software has unknown but available exploits. Unfortunately, anything but the smallest piece of code, Secure Boot Manager or Smart Card Secure Element type code, are too large to review, and it's almost impossible to flush out every corner case, which is why we obviously have to have our layered approach. We need to make sure there's physical tamper resistance and detection, whether this is at a chip level, TPM or secure element, or whether it's at a system level with the right pins coming in to check that the box hasn't been opened. We should certainly do that. And that's certainly a case that we take with our security appliances for provisioning, ensuring that they are not compromised physically. We have to provision both product supplier routes and asset owner routes of trust into our systems. Now, this is easier said than done, because with secure elements, they would traditionally go through a very constrained manufacturing process. But with industrial IoT, we obviously have a much wider aperture. And so through our secure deploy framework, we have focused very hard on ensuring that the product supplier root of trust can be provisioned correctly, or that we can harvest puff identifiers. And then the final one here is that we have to have integrity of a boot process, ensuring every device is in a node. The host device requirements, or HDRs, also come back and talk about the integrity of the boot process. This is really, really important. But how do we develop the right boot processes when all of our IoT devices are so divergent? And our answer to that is to implement a set of wizards and build tools which enable the developers to very rapidly create a high integrity secure boot, which has a known good state. It enables recovery post-exploit or suspected exploit, and remediation with signed and secured patches. But also that provides then source code rather than a black box, enabling the OEM to tailor that and to own that, to do their own reviews on the code, to walk through it, to understand exactly how it operates. You have to have both. You have to have an ease of use in terms of the functions that we're looking to implement, and the code base to go in and tailor it. We support this high integrity secure boot both on existing mainstream devices and on next generation advanced MCUs, such as ARM-based and Renesas RX microcontrollers. A good example of the advanced device technology is the ST-SFI technology I mentioned earlier. We also need to implement unique identities, and these can either be bought in from a third-party certificate authority, or we can build our own certificate chain inside of the tool, saying who am I, what is my organization, defining yourself as a self-signing CA, defining intermediate certificates, maybe for product line, maybe just the main acting certificate, and then the device ones. And every device can again be uniquely provisioned or provisioned with a group certificate. Across this, we then have to do provisioning at the prototyping and the first article stage. Again, the tools that we're seeing help with this, help to enable us to get it right before we go to volume. And in this case, we can take our code with all of the versioning information, we can sign and encrypt and export to production. We can send it out to a security appliance on our desk, or secure desktop provisioner, and from there we can program 1 or 2 or 10 or 100 devices depending on the number of production count that we've set inside the tool. So again, this has to become part of the development flow. It can't be a custom implementation each side. Then as we go to volume, we need to do secure provisioning and programming at scale. We need to enable OEMs to have a whole set of product ranges, product devices, identifiers, and all of the complexity that we traditionally have. And we're working with many partners to do this. But it has to be simple. Fast exporting of and native handling of unique crypto keys. Has to be scalable from the desktop to the global infrastructure. And it has to be secure so that we do set a hardware enforced VPN from the OEM to the chip on the programming machine in the programming factory, the far side of the world. The right tools also enable the right lifecycle management and updates. Whether again this is updating on a group key or on unique keys. We can enable this from inside the development tools. It's no longer challenging. It's part of the Secure Boot Manager and the tools to provide that. So we can load code under whichever communication channel, Wi-Fi or 5G or whatever, into an update area. Reset the device, decrypt that application and load it in, and restart the device into a known good state. No longer do you have to do this on your own. We really can commoditize a lot of these bigger challenges, enabling our customers to focus on the value in their products. So it really is about security from inception. From the point of development, getting security from an add-on into the development cycle. Security is a high-value capability. It protects high-value IP from thefts and malware and overproduction. Industrial IoT has already implemented some strong standards, and through the IEC 62443, it will define the next generation of purchasing decisions for industrial products. Ultimately, though, the right tools make security simple. We don't have to be experts because the tools will help you through the process. Thank you for listening, and I'm open for any questions. Thank you.